chapter 12 today and Wednesday. Basically, we have to talk about one more set of coordinates, then transformations, then back to applications. It sounds like a lot, but it's actually not. You're going to get your test from me on Friday. It'll be due the following Wednesday. Get it Friday, it'll be due the following Wednesday. The study guide didn't go off until, I think, yesterday or Saturday, one of the days. So I'll give you till Monday to do the study guide. So you'll have some overlap with your test and your study guide. My recommendation would be you get it done before I give out the test. But if you have time, that way you have a couple extra days. I have copies of it. Make sure I hand them out before I leave. I'm not going to hand them out now, though, because then you'll work on them instead of listening to me rant at you about cylindrical and spherical coordinates. So we're going to go ahead and get started. Review really quick of cylindrical coordinates. We know to convert into cylindrical coordinates, we have x equals r cosine theta, y equals r sine theta, and z is equal to z, right? And so essentially what cylindrical coordinates does is that when we look at the graph of a point in rectangular coordinates versus cylindrical coordinates, we have a certain amount of measure here where we take out some angle, theta, right? Distance we go out is r. And in order to get into 3 dimensions versus 2, all we do is we take the z and we elevate it. So after this, we just bring it up. And it gives us some point. And so that distance right there is z. And that's how cylindrical coordinates work. We have an angle in the xy plane going off the positive x-axis, r, the distance we're going out from the origin, the xy plane, and z, a vertical distance up to our point. And so what this gives us here is theta, r, z. The cylindrical coordinates are very, very useful if we have a shape or kind of a domain that looks like a cylinder. So a parabolic cylinder, we have all kinds of weird shapes. But this is really useful, once again, if we would have converted over to polar to begin with. What we're going to talk about today is getting out of cylindrical coordinates and talking about a whole new type of coordinates. We're going to be talking about spherical coordinates. Now you can bet that if cylindrical coordinates are based on a cylinder, spherical coordinates are based on a sphere. Easiest question of the day. Exactly right. And so what we're going to be looking at today is spherical coordinates, and to illustrate it, I went ahead and I drew something sketched out really quickly over here. The point we're going to be looking at is the point right here. Now when we look at spherical coordinates, we need to think about how we navigate on the surface of a sphere. Well, a sphere is a shape that has a constant what? Radius. When we talk about that radius, it's not just a radius of a circle, right? It's a radius that operates in all 3 dimensions. Now, because we've already used r right here in 2 dimensions, we don't want to use r again to illustrate the radius we're going out from the 3-dimensional origin to a point on our sphere. So instead, we use rho. So let me go ahead with my green marker. We're going to call this right here rho. Rho being that 3-dimensional kind of radius from the origin out to that point on our sphere. Now, because we don't want to get too confused here, we're going to use some of the same notation we use from cylindrical coordinates. That is, I'm still going to call that 2-dimensional length out r. What would this blue line be? If I'm going from the xy plane straight up, what's that going to be? This will be z, right? Everyone's okay with that? And I also have this angle over here. What would that angle be? Theta. Now when you think about the sphere, however, when I go out a certain angle in the xy plane, there's actually a whole bunch of different points on the sphere that have that angle, right? That's because going out this direction doesn't tell me if I'm up here on the sphere or down below on the sphere. It doesn't tell me where on the surface I am. For that reason, using theta isn't enough to tell me, well, how high am I up on that point? Instead, we add in another angle right here, phi. Phi measures the angle between the positive x-axis and the angle out I'm going on my sphere. So phi is our new angle. That's it, positive z-axis. So positive z-axis is out to rho, that is the distance that we're going. To right there. So what we have now is a whole new way of defining finding these points using coordinates we had in the past. That is, rather than using theta, r, and z, coming out like this, I wrote those backwards. Why did no one say anything? It's already a Monday. That was a little bit better there. Yeah. There's a test, and all of you can roll. Let me keep going. Oh, thank you. What we're going to do is we're going to translate these into now spherical coordinates. We are not going to be concerned with r because that's in 2 dimensions. Rather, we're going to be concerned with this 3-dimensional radius. So our first coordinate will be rho. The next coordinate out will be theta, that angle we are in the xy plane. And finally, c. These are what we call spherical coordinates. Tells us how far from the origin am I going, what angle this way, and what angle that direction as well. Now what we want to do is we want some way of converting between the two of these. We want a way of converting between cylindrical and spherical coordinates. And to do this, we need to look at this little series of triangles we have over here. Well, the first thing I noticed is I have x equals r cosine theta, right? So what I'm going to do is I'm bringing it over here. I know x equals r cosine theta. Oh, I can't yell at her though. Okay. Z equals Z. What I want to do is I want to derive some way of translating this over here. Well, you notice x and y both involve r, right? So really I need to get rid of r here. Because when I look at my spherical coordinates, there's no r. So what I need to do is a way of defining r in terms of either rho, theta, or phi. What I want to do is I want to look over here and see what r is. I've got r right here, right? Let's just think about this for a second. Now, I know a couple other distances on this, right? I could probably draw something out like that. And what would that distance be? What would that distance be? Well, it's taking me from the x-axis out, right? And cutting it off on what axis? What axis is this measuring distance out on? Y, right? This is kind of like y here. Okay. I could also draw something in right here. I'm going to erase it pretty quickly after I draw it so it doesn't get too confusing. What distance would that be right there? The x, right? Okay, so what I know is I've got some other distances on here. What do I know about triangles here? I know this side and this side are parallel, right? They're both going straight up in the z direction, which means this angle right here is the same as that angle right there. Are we okay with that? Two parallel lines. Back to probably 8th grade geometry for most of you here. Do you agree that's true? If I have two parallel lines and they are intersected by a single bar, I get the same angle, right? Now this gets interesting. Notice that what I have here is a z and a rho and an angle. What can I use to relate those ones? What can I use to relate z, phi, and rho? Well, if I've got this one right here, this is my adjacent side, right? And this is my hypotenuse. So what I'm going to do is, I'm trying to eliminate r, but I've stumbled across something else in the meantime. I have that cosine of phi is equal to what over what?
U over rho.
U over rho, right? What does this give me then? What do I know the conversion for? Well, I know that z is equal to rho cosine phi, right? No? There's a whole bunch of different things. I want to give you one of the triangles. Notice I've got this relationship here, right? I want you to use that idea to see if you can figure out a way to eliminate r. That is there some relation you see here that you could use the same kind of idea, the same kind of trig function or a different trig function relating R, B, and something else. Let me just a second. Let me stay at it. You guys have a little bit of this Monday. Okay, let's see here. I want to limit R, right? So I need a trig function that involves that side down there. I can use R, and if I use sine of phi, it'll be sine of phi equals what? And R over rho. What do we think? Does it look good? Which means that rho sine phi equals R, which is awesome because now I can substitute in, right? I'm going to have x equals rho sine phi cosine theta. And what is y going to be equal to? Rho sine theta sine phi, sine theta, right? And finally, z equals, and from right here, rho cosine phi. And there's other things I know based on what I know about distance and about spheres. That is, if I look at this right here, I know that phi has to be, rho measures the distance from here out, right? So I know something about distances, and that is, I'll bring it down here, a little more tip to convert here. If I'm looking at distance in a three-dimensional sense, I'm going to know that distance squared is equal to what? Have I successfully lost everyone? No, it's kind of quiet, or have I lost you? Let's do this. If I want to look at distance in a two-dimensional sense, in the xy plane, if I want the distance out to that point right there, I know I can use the Pythagorean theorem, right? That is, if I want this distance right here, I know b squared is equal to x squared plus y squared, right? Now, I'm not looking at two dimensions, I'm looking at three dimensions. So if I want the distance from here out to here, that distance squared is the distance for x squared, right? Plus y squared plus z squared. And so what I have here are three things that are uber helpful if I want to convert around. Question. No? Okay, so what I'm going to do is I'm going to bring them all over here and list them so that we can keep them on the board while we work through the problem. I know that I have, which one is it us first? X. Sine theta. Sine equals rho. Then what we're going to do first off is go ahead and look at an example here where we're going to take some spherical coordinates and convert it to rectangular. Just so we can get an idea of what these actually look like. So example, given the point 3 pi over 2, 0 in spherical coordinates, find the corresponding maybe find the corresponding, we're going to pretend like it does, rectangular coordinates.